so today we're going to be talking about what is calculus, what it is used for, why we need it. Well, there are a lot of things in math that are very, very difficult to do without calculus. For example, if you have a curve, and if we have 2 points on that curve, say I have this point and this point. It's on some coordinate system. Let's say this is the point 1, 3, and this is the point, say, 5, 4. Now, if I want to find the slope of the secant line, can I do that? Do you have the skill right now to find the slope of that line? Yes, you do. Okay. From Algebra 1, from Algebra 1, we know that, it's equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1.
Just like that.
So we have 4 minus 3 over 5 minus 1, which is 1/4. That's the slope of the secant. Okay. This is without calculus. We can do this. Now, what about if I have this another curve similar to that one, only this time I have this single point here, and I draw a tangent line. Everybody remembers from geometry the difference between secant and tangent. A secant line intersects the circle in 2 places, a tangent only 1 place. Right? So this is a tangent line. So let's say this is the point 3, 5. Can I find the slope of that line? No.
Do we have
We can go. We don't. But it's a tangent line. It only touches the curve in exactly 1 place. No, we cannot find the slope of this line without calculus. Okay? We have to have calculus to find the slope of that line. I'm looking on page 43, and it has a whole bunch of different scenarios where we need to have calculus. And remember, the third one down, does anybody have their textbook? One person? Oh, well, never mind then. Don't worry about it. I'll just keep on going. Let's see here. That's okay. That's okay. So, here's another thing we can do with calculus. Without calculus, what can we find that area of without calculus? Squares, rectangles, circles, triangles. We can find all kinds of things. We can have parallelograms, right? We can find the area of those things. That's fine, without calculus, with just geometry. But what if it doesn't look like that? What if it looks like this? Can you find this exact area? Not without calculus. Now, we can approximate it using little rectangles. Do y'all remember that from Algebra 2? When we came up and we made little rectangles and we kept doing this. Yes. Okay, but we approximated, but we had error. Yes?
Yes.
Okay, and we will approximate again this year, only this time, once we get to that point, and I think it's in chapter 5, when we get to this point. What we're going to do is we're going to use a process called a limit to make this be an infinitely small rectangles, infinitely narrow. So there's an infinite number of rectangles here, and we'll be able to find the exact area of that. Okay. Now the exact same thing happens with volume. You can find volume of many different shapes. You can find volumes of cylinders, right? Area of the base times the height. That's geometry formula. You can't do that. You can't do weird shapes unless you have calculus. So let's say you have something that looks like a cylinder. However, on the inside, it's a funnel shape. So it's this cylinder with this funnel shape cut out of it. You see that? Kind of. Generally. Okay, I mean, this is circular in here too, so it makes a shape like this. We can find the exact volume of this using calculus. Okay, there's lots and lots and lots of things that we can do with calculus. Now, on page 45, we have what's called the tangent line problem. So what we're going to do is we're going to take a shape, a curve, and we're going to say, I want to find the slope of the tangent line at this point. I want to find the slope of that tangent. So this is the point, this is the curve f of x. And I'm looking, I want to try to find m. Well, I don't know any calculus yet, so I can't find the slope. But what I can do, since I know what f of x is, what I can do is I know this point, let's say it's 4. Let's say at that point 4 that I have a height of 5. Well, let's say I come out to say 7. And I come over here and I find the slope of this secant line. I can do that, can't I? Okay, let's say this is 7, which is the point 7, say 5.5. Probably shouldn't have gone out that far. Probably would have made more sense another way. But I can find the slope of this. This is y2 minus y1, which would be 0.5 over 3, so that's equal to 1/6. That's the slope of that secant line. Well, what if I came closer? See this one. And let's say this is 6. So that's the 0.66. So what would the slope of that one be? That would be 6 minus 5, which is 1, over 6 minus 4, which is 2. So the slope of that secant line is 1/2. But what if I got closer? What if I came here to 5? And I had this one. And I want to know what is the slope of that secant line. So this is, say, 5.5 again, but that's only 1. So that's 0.5. Right, that didn't work out. I should have used a different number. It would have been better if I had actually used a function that we knew and had done this. Yeah. Anyway, what we're going to do is we're going to find the slope of this line, and we're going to keep finding slopes closer and closer and closer to this point, and then we're going to say, oh, I think it's going to be this. I'm going to guess. So that's the procedure. Now let's actually do one. Let's pick an equation, something simple, y equals x squared. And I want to find the slope of the tangent line at 2, 4. I want to find the slope of the tangent. Okay, can't find the slope, but I can find other points and evaluate that slope close to it. So, where do you want to start? Do you want to start left of the point or right of the point? Left? Okay, where do you want to start? Start at 0? Start at 1? Yeah, let's start at 1. start at 1. So we're going to get a secant line, right? So this is the point 1, 1, and this is the point 2, 4. And that's the point 1, 1. So that's 4 minus 1 is 3, over 2 minus 1 is 1. So the slope of this line is 3. Now let's take a point closer. Let's go 1.5. So that's here. And when I draw that secant line, I drew that wrong. It goes through here. Now, what's 1.5 squared? 2.25. So now I can find the slope between there and the point 2, 4. What's 4 minus 2.25? 1.75? So that's 1.75 divided by 2 minus 0.5, that's 0.5. Now what's 1.75 divided by 0.5? 3.5?
Yeah,
3.5. Okay. So we just found another. Now let's get closer to 2. How close you want to get? Let's do pretty close. Let's do like 0.1 away. Let's do like 2.9. Now, first of all, what's 2.9 squared? Oh, sorry, what? 1.9. Thank you. 3.61. So that's the point. 1.9, 3.61. Now I need to find the slope between 2, 4, and this number. So what is 4 minus 3.61? 0.39 divided by 0.1, which is 3.9. Now look at what the slopes did. 3, 3.5, 3.9. See a pattern? Okay. You want to get closer? Because I'm still not convinced. Personally, I'm not convinced. I think it's getting closer and closer to 4. But I'm not really sure. You'll do like 100th away, 0.01? Okay. So let's do 0.01, so that's 1.99. Calculator, please. 3.9601. Now I got to do the slope, so 4 minus 3.9601 would be what? 0.0399 divided by 0.01, and we get 3.99. That's the slope. Now, what is the slope at the point 2, 4? Probably 4. Okay, now we're still using algebra, but are we absolutely certain that that's the slope? No, we're still just guessing. That's all we're doing is guessing. But this is what's called the tangent problem. This is actually in effect, because once we learn how to use limits, which we're going to start that tomorrow, once we learn how to use limits and the limit theorems, then we'll be able to take the limit as this distance approaches 0. If you make that distance infinitely small, I can make this number, the slope, infinitely accurate. Okay? Because we can use point, instead of 0.01, we can have point and an infinite number of zeros in 1. And then this will be 3 and 0.9 repeating. So, and 3.9 repeating using limits can be proven to be equal to 4. So I think there's something like that on my clock, isn't it? Yeah, 6.9 repeating is 7. And that can be proven using calculus. Alright, let's see. Now, we've already talked about the area problem. And everyone knows how to approximate. Do I need to do a problem? Does everybody remember how to approximate using rectangles? We need to do it again. It's been 2 years, right? Okay, let's say we have y equals, let's do x squared. What if I want to approximate the area from 1 to 3? want to approximate that area. And I want to split this up into 4 equal width rectangles. You want to use a left, right, or a midpoint? Right? Okay. So I want 4 equal areas, so we're going to use a right. So that means that the right-hand corner, the upper right-hand corner of the rectangle touches the curve. Is this going to be an under approximation or an over? This is an over approximation. Now, where do you calculate the height of each one of these rectangles? On the right-hand edge of the rectangle, correct? So that's 2, this is 1.5, and this is 2.5. So I need the height of this first red rectangle is going to be calculated at 1.5. So at 1.5, the height is 2.25. What about at 2? What's the height? 2 squared is 4. I'm just using the equation. And then at 2.5, what's the height? 6.25. Am I right on that one? Okay. And then at 3, the height is 9. Now what's the width of each one of those rectangles? 0.5. So I have 0.5 times 2.25 plus 0.5 times 4 plus 0.5 times 6.25 plus 0.5 times 9. And that's going to be 1.125 plus 2 plus 3.125 plus 4.5. And that adds up to be 6, 7, 10 point, is it 10.75? And that's approximately the area under that curve, but it's not exact. It's an over approximation. Now, with calculus, we could do that same thing, only we'll find the exact area under the curve, because we're going to make, instead of 4 rectangles, we're going to make an infinite number of rectangles. We're going to take the limit as n approaches infinity, and that's going to make each one so narrow, I mean, finer than the width of a hair, okay? You could finer than carbon fiber, so that when you add them all up, you get the exact value of the area under the curve. It's not an approximation. And that's, in a nutshell, calculus. It's what we do. We find slopes and areas. That's, the derivative is how we find slopes, and the integral is how we find areas. And believe it or not, there's about 1 billion different applications to that. There are so many applications, we have 3 courses of it. Actually, there's a lot more courses than that. There's after calculus 3, there's differential equations, and then I took also in graduate school advanced calculus 1 and advanced calculus 2. So I've had 5 different calculuses. But there's so many applications to calculus, and other than there's business calculus. They have 2 classes of just business calculus, business cal 1 and business cal 2. That everything done in business these days with markets and profit and cost, everything is done using calculus. Because calculus is just a set of tools that helps you make difficult mathematics and make it much easier. Okay? Alright. So, your homework is 1 through 9. On page 47.